Hello, I'm going to show you how to process a cardiac scan. First, we're going to highlight the patient. If we go to list series, you can see we acquired a resting study and a stress-gated study. It acquires the stress and the stress-gated simultaneously. So even though there's 3 files, there's actually only 2 sets of images acquired. Okay, so we're going to have the patient highlighted, and we're going to go under the cardiac category, ADAC cardiac processing. This tool is going to correct for motion if needed. It's going to reconstruct the raw data using filtered back projection, and then it's going to slice the images into horizontal long, vertical long, and a short axis slices, and then we're going to load all of that data that's reconstructed into another program to actually analyze it. So the files are loaded up and we have check marks all the way down. We want to first start at the top with data selector. Just so happens to look like the resting data didn't get bucketed correctly. It's a common problem. It probably has a input name that was incorrect, but so we have stress, stress-gated, and rest, which are all loaded incorrectly. And when we go to quality control, we can see rest and stress. Here's rest, here's stress. If you want, you can make it bigger, check for motion. You can look at the sinogram over here. Before and after, that's before and after motion correction. We haven't done any motion correction, that's why they're identical. There's also a linogram and a sum image. We want to put the line in the middle of the heart. You can move it to a couple different parts of the heart and check the sinogram. You want to see a nice smooth sinogram for both the rest and the stress. If that line isn't in the middle of the heart, your sinogram is going to be useless. Putting the line in the middle of the heart is also useful because it can help you determine if you need to motion correct. We do not need to motion correct this patient. If you did need to motion correct, you would click the motion correct button, move this little red box over the heart, and then it would then correct for motion. If you have a patient that has no motion and you motion correct them, it will actually add motion to the image, which is odd, but that's what it does. It tries to find things that don't need fixed and fixes them. But anyhow, that's how you would do it. If this patient had a ton of motion, it would actually look like this to begin with and look like this afterwards. But if you hit OK, it's going to save that crappy motion correction, which we do not want to do. So I'm just going to hit revert to original, go back to what we know is good. Okay, so this first tab here is it's just a Tomo processing. Don't worry about this. Move to auto cardiac. It's more information than you need to know. This auto cardiac page, this page is used to reconstruct the heart. So if we click on the settings tab, it's going to do a filtered back projection, and it's going to use a Butterworth filter with an order. I'm just going to click this real quick, with an order of 5 and a cutoff of 0.6. If you want, you can change the order here. 5 is common for resting cardiacs. You can change this here. You can see the amplitude and Nyquist changing as I change the order and cutoff. You can also change your filter here if you want. We're just going to leave it on Butterworth. We'll go over all of this in class, but currently I'm not going to change anything. Okay, so, and this filtered back and filter and all this, that's for the gated stress. I can change it to rest. And as you can see, the settings that we have for the order and cutoff are a little different for rest. Change it to stress gated, and so on. So if you like, we'll go over all that later. But that's how you change the different items. That's how you would change the filters, and that's how you would change the reconstruction. We're going to go back to reconstruction. Now, these images that are located here have really bright pixels in the liver because of the patient's liver uptake. The pixels inside this yellow circle are normalized to the hottest pixel in that region. So if we put that region over the liver, it renormalizes it and lowers the counts across that area. So we want to cut out all those hot liver counts so it renormalizes the heart correctly. We'll go over all this in class. So, and you're going to learn how to do this. This technique of processing hearts is going to be learned in the clinic, but I'm just going to show you how to use the program. So you draw your regions of interest around the heart in the stress-gated rest and stress here. Or actually, I'm sorry, I misspoke. It looks like we have stress, rest, and stress-gated down here. And we're going to line the horizontal long axis. We want to make them all look identical. It's a nice resting image. Okay. Now when we go to masking and centering is kind of like your fine-tuning compared to your reconstruction. It allows you to zoom in on that area that we've been trying to draw a nice tight region around. You want to put your crosshairs right in the middle of the left ventricle. So now that we have this masking and centering done, when we go to flexible display, it's going to display the stress over the rest, which is common, with a short axis, vertical long axis, and horizontal long axis, which is labeled here, here, and here. If you right-click in this bar, just like on a bone scan, you can change the lookup table to warm metal, which is kind of a common lookup table to use here. And if you click on the image, you can scroll through the individual slices. If you click right next to the green box or the red box or the blue box, it moves one frame. If you click all the way out here, it moves 2, 3, 4, it moves 5 frames. And you want the stress and the rest to be cut exactly. So you don't want this doesn't match up with this, so we need to make it match up by clicking here. Okay, so now each one of these slices is matched up perfectly, so the doctors can look at the blood flow throughout the left ventricle in each individual slice across the short axis, across the vertical long, and across the horizontal long. And you also want the apex, which is located right here, to be facing the same direction in both the stress and the rest. You don't want one apex pointed down here and one apex pointed up here. You want them to be perfectly matched, which they're pretty matched here. Once you're done, you hit complete. It's going to save all those reconstructed files, and it's going to automatically launch these CEDARS programs. So, see that little icon just switched over. So now when I double click on it, it's going to load up the QPS page. This is what's called, I believe they call it tertiary software. It's not made by Siemens, but it's installed on Siemens. So let's see here. So basically what this is saying, we have to compare, we have a database of known healthy patients that we want to compare these slices of this patient's heart to. So we want to label this patient with the correct isotope, so we're using MIB, which is Cestamib, which is MB. If we were using tetrafosmin, or thallium, we would select TL or tetrafosmin. If this was attenuation correction, you would select AC. If it was a female, you would select female. But in this case, it's a male with MIB, and this was a stress image. And this is a male resting with MIB as well. It automatically chose these correctly. What it did have a hard time determining was whether or not this resting image was rest, so I just had to click rest and tell it that that's what it was. So I hit OK. So now when we go to Splash, we can look at the same thing that we had pulled up before, but we can compare all of this information that's here to a database of normal, which I'll again go over in class, but these bullseyes, as you can see, we want zeros across the board. This patient in a few different areas has ones, or in other cases might have twos or threes, which means that the patient's heart might be slightly ischemic in the areas that are represented by these bullseyes. So this program tells you, say, the volume of the left ventricle. It tells you, let's see, what's some other good information they look at. It reconstructs the left ventricle into a 3D map. It applies then the uniformity of the isotope to that 3D map so they can look at it to see it looks like the apex is a little low on counts. But primarily they're using the splash page and the raw page to assess for motion and to assess for even myocardial distribution of the tracer. So I'm going to go to print. Okay. Exit. Complete. It's just going to take a screen save of that for me for later. Now I've got QGS. I can either double click on it or I can click launch. This is the gated data. This is the same program. This is the same company, just a different program. And this program is loaded on top of a ESOF program. That's why I loaded up that Siemens ESOF program temporarily. So if I go to Splash, you can see a splash of the gated data. Now gated data is lower in count, so that's why it looks so bad. If we go to results, I can even turn on the gate so you can see the heartbeat. But you want to make sure that here where it says ED, that this says ES, which is not always the lowest frame. So if you do gating, you want to make sure you flip it back to that. And then this has the ejection fraction of the heart. It also shows a lot of other information like the stroke volume and other data, but we're not going to go over that right now. I just want to make a save screen of this, so I'm going to go to print. Okay. Exit. Complete. So now when we refresh our patient, we go to heart, list. I just made a save screen. Whoops. Of the QGS, save screen of the QPS. Now, here, let me get that back to the way we had it. There we go. So these are the three files I started with. Those three files were then reconstructed to these files, and then these files were located into, or were loaded into these two programs to then generate these two snapshots. The doctors don't even really need to see the snapshots. We're going to transfer them, the data that we reconstructed, plus the raw data. Now when we send that data to them, they're going to load it up into their own QGS and QPS tools, and then they'll be able to assess the function of that patient's heart. There's other third-party software that can be used to analyze cardiacs. 4DM is one of them, and CEDARS. Those are the two main ones that I can think of off the top of my head. Okay, I've gone over MUGA processing, which is here. Planar stress rest is very rare and most likely will never be seen. This would be resting only. If a patient wasn't able to finish the stress test, you could just analyze the resting portion of the data. And then these two are for a newer camera, Symbia camera, but they're basically the same as this. It's just a newer version of the same software. And this is a non-gated stress. Occasionally a patient's heartbeat is so abnormal that we're unable to gate the stress portion. If that's what happens, we don't use this tool, we just use this one. So that I've just explained all the cardiac programs that we have here and how to process a standard stress rest cardiac. Thank you.